Hi, I will now explain to you a couple of proofs here of no cloning, conservation of information, and perpendicularity of observables. Okay. These I've done in a notation that I find easier because I don't jive well with the rack bra and cat notation. Especially for something like this, I think it's just too overloaded, too many symbols to say something that's not that shouldn't be that verbose to say. Okay, so here we go. Let's begin with the basic no cloning theorem. No cloning theorem, as it's usually presented. Again, I'm not totally sure. I should really look at this because, for example, this is, you have a state here in an environment, right? So this is a tensor product, UE, and I don't know if if you should just go from UE to UU, let's say, or if really you should have like UE, and then you should go into UU and some other piece of the environment that's left, right? It's not necessary, I don't think, for the whole environment to turn into a U, but rather, only one part of the environment, right? I also notice that if you do take this this point of view here, right, in order for this thing to turn into UU, that means that the first and second Hilbert spaces in the tensor product are the same. But anyways, that being said, let's do the short, succinct story, which is anyways what I want to tell you. When you see this little arrow here, it means that UE by unitary evolution, right? It turns into UU, and so it's this right here, right? U of UE equals UU. So this arrow here just means that there's a unitary map that sends one to the other. All right. That being said, so let's say UE. The result of a unitary map gives you UU. In others, Zurek says the unitary map that applied to UE gives you UU, and that the same unitary map applied to VE gives you VV. Okay. By unitarity, then, the inner product of this with itself ought to be the same thing as the inner product of that with itself. So you have here that UE comma UE. It's just this right here, which is UU comma UU, right? And these things, by the way, are not bra and cat, but they're just the mathematicians basically the inner product in the Hilbert space, okay? And the Hilbert space that you're using there is that tensor product Hilbert space, okay? But that we know that breaks down into this product, right? Where the inner products here are now this inner product is the inner product of the first Hilbert space, and this other one right here is the inner product of the second Hilbert space. Okay, so we have that this above here is really just equal to U comma U E, and that by this side is equal to U comma U comma U. Okay, since U is a non-zero vector, you can eliminate the U comma U from both sides, and you get that E comma E equals U comma U. Similarly, exactly the same argument, just replacing U by V, you get that E comma E is also equal to V comma V. Now, again, by unitarity, the inner product of this with the one that's below ought to be the same thing as the inner product of this with this. So we have that UE, inner product VE, is equal to UU, inner product VV, and we know that by the splitting of the inner product, just like we did up there, that's UU times EE is equal to UV, UV. Sorry, UV EE is equal to UV UV. Now this UV may be 0, right? We don't know that. So there's our options. So you have either U comma V is equal to 0, or besides then you have that EE is equal to UV. Okay. Now it turns out that if you have two vectors such that UU is equal to EE, VV equals EE, and UV also equals EE, that implies that U and V are the same. Here's the argument for that. Okay, So let's take u minus v, inner product, right, with u minus v. What does that give us? Whatever, u, right, plus vv minus 2 u inner product v. Remember that in these Hilbert spaces, right, the inner product of a vector with itself is positive. It's not like in Lorentz. And also once you have that situation, you know, where if a vector dotted with itself is 0, then that vector is the 0 vector. So we have here UU, we knew by previous hypothesis, that's EE. This guy is also EE, and then minus 2 EE. That whole thing gives you 0. So therefore, U minus V dotted with itself gives you 0, but then that means that U minus V is the 0 vector, so U is equal to V. Okay? So there we concluded that if the evolution is unitary, like so, you know, then either U and V are orthogonal to each other, or U and V are the same vector. Okay. Now I'll show you the what I call the cloning theorem with a little bit more bells and whistles. Okay. There you have the same thing as before, right? But you have here the possibility of having a complex unit number in front of this that comes out. And when you do so you do UE, and it gives you alpha UU, and then you do VE, and that gives you beta VV, right? Same as before, but with this alpha and beta, which are unit complex numbers in front. Okay. Now the same thing as before, right? And I will abbreviate by doing this, by saying, you know, just from this, by unitary, U squared E squared is equal to alpha squared times U squared U squared. Okay. By the way, I missed here a U squared. Okay. And here the same story, right? That V squared E squared is equal to just this beta in front, beta squared, times V squared times V squared. Again, I missed a V squared here, but it doesn't matter. At the end, what happens? One of the U squares, you know, gets canceled out here, and therefore you just get that basically that E squared is equal to alpha squared times U squared. And then from here, the same story. In fact, let me just write this in here: U squared and then V squared. Okay. So the same story, right, as before. In other words, this, since U is not 0 and V are not 0, this U and this V cancel from this side, and you get that E squared is equal to alpha squared U squared, and that E squared is equal to beta squared V squared. Okay. Now let's take the inner product of these two. All right. So there you get, you know, a UV EE, and that's equal to the inner product of these two, which, remember that one of these constants pulls out with a complex conjugate because it's like a Hermitian inner product, and then you get that, you know, alpha a star times B, or alpha conjugate times B, equals this, right? UVV by you know, when you do the inner product of these two, it splits into the product of the two inner products of the single Hilbert spaces. All right, so you get this right here. All right. And now, again, if U comma V is 0, then you can just cancel this. Sorry, either U comma V is 0, or if it's not, you can cancel these out, right? And you get that E. If U comma V is not 0, if the inner product of U and V is not 0, you get that that E inner product E is equal to this complex number here, right? But you can move the complex numbers back in, and you basically get that E inner product E is equal to alpha U inner product beta B. But note from before, from looking at this, that also E comma E inner product E is just equal to alpha U inner product alpha U, and also from this one that E inner product E is equal to beta B inner product beta B. So by our previous argument that we used here, you get that basically that then it must be the case that alpha U is equal to beta B. So in other words, U is equal to a complex number a complex unit number times v. So basically that means that u and v are physically equivalent. Okay, so that's just, you know, the same no cloning basic theorem that I showed you first, but with more bells and whistles, you know, with that extra possibility that you could have those unit complex factors in front. All right, so now let's do conservation of information. Okay, so that just means that if you start with two different initial states, you won't get the final state. So in other words, anytime you have a state, you can always trace back to what the initial state is. So we have then that the following. So imagine that you start with a state u and you end up with a state w. This is sort of like a proof by contradiction, right? And then let's say you start with a state, although not really contradiction, you're just going to get the conclusion that u and v must be the same. You got v, it also by a unitary map gives you w. You know, they say v evolves into w, or just, you know, unitary map applied to v gives you w. And same of u, the same unitary map. Okay, so now take the inner product of u and v. Well, that's the same thing as w inner product w, right, by unitarity. Also, by unitarity, u inner product u is w inner product w, v inner product v is w inner product w. So you get these three things, and we saw from before that whenever you have those conditions, right, then u and v must be the same. So in other words, a w basically, you know, determines what state you started with, or you can trace backward. Now I saw this, you know, this argument interesting or whatever, but then also you think about it back and you're like, wait a minute, isn't that just saying that basically the unitary evolution map is one-to-one? And I thought that's one of the properties of unitary maps, that they're invertible. Maybe I'm wrong. Maybe I don't remember you know, my operator analysis that well, but I think that was one of the conditions for unitarity. So it's almost like from that you almost don't even need this. But anyhow, that's that. It's still, you know, worth doing, I guess, in observing the various ramifications there. So all right, and then this result right here, very similar in feel also. It says that different results of observations must be perpendicular. Okay, so this I got from a talk by Zurek, and the proof he gave there had a lot of factors and using real and imaginary parts of complex numbers and stuff. But I thought that maybe it could be done a lot easier, you know, a lot simpler, like this. And again, it's got, you know, a lot of the feel of the previous thing. So let's see what happens. There you have that. You have again a composite system, right? So you have, you know, a tensor product there. You have u and e. So u is the thing to be measured, and e is, let's say, some state of the measuring apparatus, right? And that, you know, after some time, right, you know, the measurement somehow gets done, and you have that you have ua, right? So in other words, here you assume that the system stays in the same state, but that the apparatus goes into some state A. Then you feed it another state, right? So you again have a different state with the same initial state of the apparatus, and then you say that evolves into, again, keeping the state stays the same, the v, but that the apparatus then goes to a possibly different thing from A, right? A possibly different state v. And in fact, you hope, right, that the states are different so that you can distinguish between one state and the other. All right. So again, by using previous technology, right, you know that that this map, you assume rather that it's unitary, and therefore you can use all the stuff that we've done before. And you have that v squared e squared equals v squared b squared. So then e squared is also equal to b squared. Now you take the inner product of these two, and again, by unitarity should be the same thing as the inner product of those two. So UE comma VE ought to be the same thing as, UA inner product of VB, right? And then by the fact that the inner product in the product space splits into those two inner products in the constituent spaces, you have that U comma V times C comma E is equal to U comma VAV. And now you again have two choices. Either U comma V is 0, which makes that true, right? Or you have that E comma E is equal to A comma V. But again, by the previous things that you should have already learned, if you understood the beginning half of this facts that I'm telling you here, you have that then A must be equal to B. So either U is perpendicular to V, or A is equal to B. So in other words, if there's said to be even the tiniest difference in the instruments, so in other words, if you can at all slightly distinguish between U and V, then automatically U and V are perpendicular. Okay? So, and then in Zurek's talk, he actually goes on to do a lot more very interesting things and so on and so forth. But I just wanted to tell you, the basics in a notation which I think is very simple and direct. Thanks.